the thingies. What? The lab? Yeah.
You said it's not like a real rainbow where you can take out the color and make a t-shirt out of it. Can you do that with a real rainbow anyway?
No. No, we're going to make rainbows, but we can't pluck out the colors from the rainbow.
Does it say
Sorry.
any or many? Any.
Any. For light, as for any EM wave, wavelength is related to frequency. Okay? And we say that it's related to frequency by lambda equals c over f, where c is the speed of light, f is the frequency of light, and lambda is the wavelength for that light. Okay? You know, if you want to see it in a nice universal wave equation formation, you might also say c equals lambda f, and that's the format we wrote it last year. However, in a medium other than a vacuum, so when we're actually in a material medium, the speed of light changes. And it's dependent upon the index of refraction of that particular medium. So the wavelength in a medium, let's call it medium n, is equal to speed of light in a vacuum divided by the index of refraction for that medium divided by the frequency of the wave. And you might want to rewrite that as, and I'll just do it as a poor form mathematical continuation here, C over NF, which is the same as if C over F is the wavelength in a vacuum, then we could just say that it's the wavelength in a vacuum divided by n. Okay, so if I want to know the wavelength of a light wave in a particular medium, I could approach it one of two ways. I could say the wavelength within a medium is either equal to the speed of light in a vacuum divided by the index of refraction times the frequency of that light, or I could say the wavelength of light in a particular medium is equal to the wavelength in a vacuum divided by the index of refraction within the medium that the light is currently found. Yep. If we lived in a really thick glass bubble, like if we were creatures that could move through liquid glass.
Like if one person were just like stuck in a really thick glass bubble.
Well, if you were somebody that was living in a really optically dense medium, okay, then it would take a lot longer for the light to get to you. So yeah, I guess you would see things happen around you at a delayed rate compared to everybody else. But then, as soon as you came out of that bubble, you'd see things at the same rate as everybody else. Yeah. All right, so we say that the wavelength has been reduced by a factor of n. Where n is the index of refraction. And what we were just talking about on the blackboard was a scenario where you have light shone at a thin film. So I want to reconstruct that a little bit. How you could maybe physically set up that kind of scenario. Can I take this away? Yep.
Is EM electromagnetic?
EM is electromagnetic. All right, let's take this away. 1 over n. All right, so experimentally, physically, we could set this up as being a thin film found between two slabs. Okay, and this is a little bit Mickey Mousey. Obviously, the angle may not be this extreme if I'm making a thin film. But in between these two slabs, we're going to say that there's a certain thickness. That's our film. It's got a thickness T of air. Okay, so I'm going to ask you to draw this, if you haven't already. So we've got two glass plates and a wedge of air. So I'm going to have an incident ray. Now this ray, I'm going to draw multiple colors here, but each of these rays is going to be the same frequency of light. Okay, the colors that I'm introducing isn't to say that the ray changes color. It's just so that we can keep track of all the vectors and things that are going on. So I've got this ray that comes in. I'm going to call it vector 1. And vector 1 hits the top surface of that wedge of air, and it bounces off of the top surface of the wedge of air.
How would you know for the thickness which part? Because like, isn't it a different length?
Oh yeah, that's actually one of the things we're going to get to.
So
The
just
thickness
put it
varies.
anywhere.
Yeah, we're just going to be arbitrary for now. Okay. Some of the light actually gets into the air, though. Gets transmitted into the air medium. It gets through. And that light may reflect off of the back edge of the air. And we're going to call that vector 2.
Wouldn't some get reflected off the front edge?
Yeah. So here's the light that's getting reflected off the front edge of the air. And this is the light that's getting reflected off the...
I'm talking about like the...
Oh, of the glass?
Yeah.
Yeah, we're not even considering the glass right now in terms of reflections. Okay. Now, as it turns out, if you take a look carefully at this, and we discussed that we're really not talking about light being shone at an angle here, we're talking about light being shone straight on. If this light is actually shone straight on, we've only drawn it at an angle for simplicity purposes, for expressing the ideas. But if this light was shone straight on, then the blue ray, ray 2, would have traveled twice the thickness in terms of its extra distance relative to ray 1. Can you see what I mean by that? It's traveled 2 times t further through space than vector 1. It had to go through the wedge once, then back through the wedge again. So its extra travel distance, its path length difference, has been 2 times t. So 2 I always get that messed up. 2 L's and traveled?
Yeah.
Looks better. Not sure if it's right. Okay, 2t farther. Okay, vector 2 has had the opportunity now to travel for an extra 2t in terms of distance.
Farther than 1.
Then 1, sorry, yeah. Okay, let's put in a little piece of trivia here, and we talked about it with the wave demonstrator, but I'd like to put it into writing so it's sort of formally together. When a wave reflects off of a higher index material as it travels from a lower index material. Now, instead of talking about it in terms of inversions, I want to talk about it in terms of phase shifting. It experiences a change of phase of a half wavelength. Okay. That's just to say that there's some inversion properties happening here. Now, if we're talking about high index of refraction, is that going to be slow speed or high speed? Okay, let's keep that on the back burner. So as I experience this reflection off the back surface here, I'm going to have a phase shift of a half wavelength. And as I reflect off the front surface, no phase shift. Okay? We also said that the blue ray here, ray 2, is traveling an extra 2t farther than the orange wave here, okay? So the extra number of wavelengths that would have to fit in as we go through here, back again, or the extra distance rather it would have to fit would be 2t. That would have to travel rather is 2t. And I want to bring up this equation here, and we can come back to it. Oh, sorry, minus 1/2. Yep.